Hello guys, welcome to the video. So in this video I want to talk about a very interesting question, like a kind of like a deep foundational physics question. And of course the trouble with this kind of questions is that it's not really, it can either be some really great insight, rarely, or it can be just some philosophical rabbit hole that just like, and that's why I'm doing a YouTube video, because for a YouTube video, I mean, both are actually good, because even if it's a philosophical rabbit hole, some of my viewers are definitely going to enjoy that. We will have some insights because not everyone is here for just for physics. I know that. And that's why I thought it would be good to have your, like, even if some of you watch and if you have some insights, some, if you want to share, I would really love if you do that in the comments, because it's not just I want to tell you about my thoughts, but I also want your feedback if that's possible for you, and if this question interests you, because maybe just maybe I am totally off in a wrong direction. So yeah, but yeah, I'll just tell you what I believe is true and why and everything. So the claim I want to make is, oh, not a claim maybe, but the point of view that I want to push forward in this video is that geometry is, well, let's start this way. Geometry is more fundamental than we believe. So, first of all, this actually boils down to a much deeper question, that is mathematics invented or discovered? Or even deeper, what is mathematics? Especially from the perspective of a physicist, because I am a physics student, and well, technically the work I do, the research I do, it's everything. It's some of it is interdisciplinary, but it's mostly physics. So if I had to like describe myself in one word, I would say I'm a physicist, not a mathematician, not something else, not a philosopher. Well, those are my interests, but I am a physicist. So coming from a physicist, this question is even more interesting, because some or even many physicists tend to see mathematics as a tool. Well, it's just a tool that we use that makes the description of reality easier. And that doesn't mean we want to, the people who say this, I don't think they do that to downplay mathematics, because it is the only tool that works. So it's not like it's a tool, but if I didn't have this tool, I would have used some other tool. Well, I don't think any sensible physicist believes that, because mathematics really is the only tool that works. I mean, without mathematics, without the mathematical techniques, what other tool can you think of? Philosophy, that would have derailed physics. I mean, no other tool works for physics. So it's definitely the only tool there is. So calling it a tool is a bit, I should say, downplaying the role of mathematics. But yeah, technically the idea goes that it's still a tool, in the sense that mathematics is not really dependent on physics, because the mathematical arguments do not work because of this physical reality, or what we observe in the physical reality. It's not like it has been fine tuned for that. Those are valid arguments in themselves, and we could apply this to physical problems. We could apply this to even imaginary, like counterfactual problems, some a system that doesn't exist in our universe, for instance, or a system that is not possible in our universe because it violates some laws of physics. But if we hypothetically imagine such a system to exist somewhere, hypothetically, we could still apply the laws of mathematics there and just study the system. Of course, the results would not make sense to physicists, because that's not true in our universe. But yeah, that's the point. And this goes to the deeper question, then what is mathematics? Is it something more fundamental than physics, or than this entire universe? And that's the question. So that's something I will briefly touch upon near the end of the video. But for now, because this is something I've already touched upon in some of my previous videos, writings and stuff like that, so I don't want to start off with that. Okay, but the main question that I would like to address in this video, as I told you, and this is something I have not done previously, because it's like I recently thought about this, is the geometry aspect. So okay, for now, let's not argue about whether mathematics is a tool or something deeper. Okay, let's say mathematics is just mathematics. And there are many mathematical techniques, many mathematical tools, many mathematical categories, of which I am no expert, because I'm not a mathematician. But roughly speaking, if for the purpose of our discussion, let's just focus on geometry and algebra. That's it. So algebra is really fundamental, by the way. Algebra is not just well, some boring kind of mathematics you do in high school. You use algebra at every point, especially if you're a physicist. You use algebra every time without even realizing you're using algebra, right? Because what is algebra basically? It gives you a relation between two variables. One of them, usually one of them is a dependent variable, one of them is an independent variable. So let's say y equals 3x. That's an algebraic equation. So that tells you how y varies with x. So if you know this equation, you can manipulate it. You can find x if you know y. You can find y if you know x, and stuff like that. You can plot it on a y versus x, and you can take its derivative. You can check you can do lots of stuff. Well, y equals 3x is a very trivial example, but you see what I mean. This algebraic equation can be way more complicated than this. So, and of course, there are other, like, I'm not going into more realistic scenarios like integral summations and stuff like that. No, they are not technically, like, not what people understand by algebra. Well, integral is usually a bit like it's thought to be a part of I mean, it is calculus more than algebra. But what I'm trying to say is that just for a moment, think about geometry as something. Well, we know intuitively what geometry is, like something you can visualize. You can, not really a plot, by the way. A plot of an algebraic equation is not geometry, to me at least. Yeah, the plot can have interesting geometric patterns, of course, but it's just a representation of an algebraic equation. So if you plot y equals x square and you get a parabolic shape, that's not geometry. That's still algebra. That's a visual representation of your algebraic equation. So that's not what I mean by geometry, at least for the purpose of this video. For me, geometry is something which is in itself, without depending on any kind of algebraic equation or any kind of mathematical equation or inequality or expression, whatever, like just to give you the basic idea, it's a pattern in itself. So, well, I mean, to me, geometry is the way I'm thinking about geometry might have closer links with group theory than with this traditional algebra. But of course, everything is linked more or less in mathematics, not cleanly linked. You may have heard of the Langlands program in mathematics, for instance, but anyway, let's not get there. But the point is, well, okay, maybe I'm just beating around the bush a little. So for me, geometry means simply, I'll give an example that will clear things up. You are playing with the rules to create some pattern without worrying about like the exact equation and stuff like that. You see, that's why I'm saying this idea may not, maybe I'm missing something important, maybe this is not really accurate. That's why I want your feedback. That's why I'm not claiming this to be correct, and that's why I'm making a YouTube video and not because, well, I think it's just a matter of having an open discussion with my viewers. If you're ready to engage, you can comment down below, of course. Yeah, now the point is, why do I think geometry is more fundamental than algebra? Again, this is it's a bit geometry is more fundamental than algebra is not really a valid statement in itself, but by geometry, what I mean by geometry here is more fundamental than what I refer to as by algebra here. That would be more accurate to say. Now, I'll give you some examples. So, many times we use algebra, but in my feeling, in my view, actually what we're doing is that just because algebra is more practical to use for that particular system or that particular whatever, but actually there is still geometry hiding somewhere. That's my feeling. Now, in physics, specifically coming from a physicist, let's talk about Einstein's theory of general relativity, which is really the most successful theory of gravity, and it's one of the pillars of modern physics, of course. So it's purely a geometric theory. Einstein was trying to find a theory of gravity. Before Einstein, Newton did physics. Newton didn't do geometry. Newton did physics. He said that you have two massive bodies, m1 and m2, and the distance separating them is r. So he gave a simple law. The gravitational force of attraction between these two bodies is proportional to their masses, and it's inversely proportional to the square of r. So m1 m2 over r squared. And this square of r is it was not guessed by Newton. Actually, it came from, there were already some evidence from empirical studies. Like, for instance, Kepler already gave this law about the time period of revolution of a planet and the radius of the orbit, stuff like that. So there was some reason for that for Newton, because you could have seen that, okay, so Newton had the intuition that if the bodies were very far apart, then the gravitational force would be low. So, but he could still make it like m1 m2 over r, why r squared, or maybe he could even make it r cube if he wanted an even more nonlinear, like more drastic effect. So the r square had a reason, of course, but Newton's theory is still in a way built by hand, because you couldn't derive it exactly. You cannot derive m1 m2 by r square. You can see why it makes sense, why it works, but you cannot derive it. Like, maybe not derive, but what I wanted to say is that you cannot really show that this is the only theory that would work at Newton's level. Because even if you wanted to formulate a theory of gravity with a different power of r than 2, like instead of r squared, but in the same framework as Newton, it would still have worked to some extent. But the thing about Einstein's theory is that it's very rigid, and rigidity is sometimes good in physics, sometimes not. But yeah, in this case it's good, because in Einstein's theory, you definitely, I mean, if you take the classical limit, the Newtonian limit, if you ignore the relativistic corrections and the more subtle aspects, then you see that it had to be r squared, because r squared relates to the curvature. Well, what is the curvature? Curvature is, if you have a circle of radius r, the curvature scales as 1 over r, the inverse of r, the reciprocal of r. And if you think about it, if it's like a more continuous curvature, then you have you I mean I cannot give you the exact mathematical argument in like verbally, but it's 1 over r square is a very good argument. I mean, you can even try to think about it intuitively. You have a sphere. What is the surface area of a sphere? It's 4 pi r squared. So 4 pi is a constant, so it scales as the square of r. It scales as r square. So so if you want a spherical geometry, you must have r squared. You cannot say that let me see if I can get something like a sphere, but with a surface area that scales as, let's say, just r or r cube or r to the power something else. You cannot get it. It's very rigid. Geometry is rigid in this sense because a sphere is a sphere. If you mess with it, then it will no longer be a sphere. It will be some distorted shape. And that's the thing. Because if you have a theory that works, Einstein's theory works. Einstein's theory has been tested against predictions, against experiments, like against observations, not really, yeah, observations. It has even predicted phenomena like that star, that thing, that dwarf, the eclipse or something. I forgot the exact. Yeah. So if you have such a successful theory, which is on top of all of that, it is very rigid. That means Einstein's theory, the framework will completely break if you try to mess with the parameters, which is a good thing in a way. Because that means, indeed, this is how gravity works. Because if it was just like, oh, gravity is, Einstein didn't really understand gravity. He just gave us a theory, but this theory is not really rigid. Because even if I mess with the parameters, it still works. That means, what is special about Einstein's theory? Why should physicists claim, like, accept this as the theory of gravity? This unique and the minimal theory that can describe all the aspects of gravity. Because it's rigid. Because if you try something else, it will break. That's it. So this is the thing. So that's a purely geometrical example. But now some of you will tell me, okay, gravity is one part of physics, but the universe is so much more than that. I mean, I myself don't work in gravity, for instance. I work in the physics of complex systems, the physics of living matter, which mostly involves statistical physics and sometimes nonlinear dynamics and simulations and more messy stuff. So it's rigidity is not always a good thing here. That's why I said it's not always good. Because, well, this is a very new field, very growing field. Here we don't even know what we're doing for the most part. That makes it more interesting, but at the same time more well, in a way challenging. But that depends, because in gravity, in pure gravity, there is very little to do foundationally. That's the thing. The guys who are working on theoretical cosmology, well, I mean, the questions they're trying to tackle are so big that they cannot even hope for any falsified, like any experimental validation. And if you really want to work on the foundations of gravity or even quantum mechanics, there is very little to do, because the foundations are actually either strong. In case of gravity, the foundations are really strong. So that's why people are working on gravitational waves. For instance, gravitational wave astronomy. Machine learning is really like the talk of the town now. I mean, because that's something new, and that's like when you have data, like you work with lots of data coming from the telescopes and stuff like that. Something that has never really interested me personally, but yeah, that's a very trending topic nowadays. Because, well, that's not real physics. I mean, you're not well, that is an important job. I'm not saying that that's not important, the guys who are doing it, but at the same time, that's not foundational. You're not trying to create a theory of something. You have the theory, you have a very standard framework, you have Einstein's field equations, you have the for instance, the, what do you call it, the Friedman equations, the universe expanding. Like, what I'm saying is that you have a very rigid framework, and you don't really have any reason to believe that this framework is incomplete or incorrect, so let's try to make a new theoretical framework of the universe. No, that's not what anyone is doing, except if you, well, that's not a reasonable path to explore. So that's why we are working on incremental research. Like, there's already some people have done this, so let me see if I can just tweak some parameters and get a new result, and that kind of thing. Or maybe I have a lots of data, so let's see how to use machine learning models to fit the data and find some new, well, what is the age of that star, or what is finding signatures of black holes and other exotic phenomena, cosmological objects, or even finding signatures of gravitational waves. All of this is very exciting, very important research, but at the same time, they're not foundational. Quantum mechanics is a bit, well, again, quantum mechanics, some people are actually working in foundations of quantum mechanics. Is really, I personally believe it's very important to work on foundations of quantum mechanics, because unlike the general relativity, here there are actually some open questions which have not been answered yet. Even the quantum mechanics is over 100 years old now. The formulation, the standard formulation is over 100 years old now. There is no consensus. So, but again, some people claim that these questions are just like philosophical questions. There is nothing to be gained from working in the foundations of quantum mechanics as well. And yeah, definitely it's not a very, if you think from the career point of view, it's not a very lucrative option at all. So even in quantum mechanics, people are moving more into applied or technological aspects like quantum computers, quantum information, and stuff like that. Or like quantum dots, technologies like quantum dots, or more like low temperature stuff like that. superconductors, even they're all like in a way involve quantum mechanics, direct consequence of quantum mechanics, in fact. So now the question is, what about yeah, what was I? Yeah, so you can say that quantum mechanics is the other pillar of physics. Gravity, fine. You say gravity is geometry. We can agree that Einstein has already proved that. But now you're saying that geometry is the most fundamental, maybe the most fundamental framework of the universe itself. But the universe is not just gravity. What about quantum mechanics? Where is geometry in quantum mechanics? Well, this is me maybe stretching myself a bit too far, because I don't really have a mathematical argument at this point, and I don't know if there exists one. But even in quantum mechanics, that's what I'm saying. Quantum mechanics is mostly linear algebra. It's not really geometry, in the standard way what we understand by geometry. But I'll give you some examples. Don't worry about it, because my point is geometry can sneak in. Like geometry can always underlie algebra, but the other way around, I don't really think so, because algebra is just a way to represent the well, that's just my personal feeling, but I'll tell you what I mean. In quantum mechanics, you are doing linear algebra, so I'm sorry. Maybe I got too excited. Sorry. Yeah. So where was I? Quantum mechanics is about linear algebra, yeah. But what is linear algebra? You need to define all this idea even before the Hilbert space from formalism and everything. You have a vector space with an eigenbasis, like eigenvectors, eigenvalues, corresponding eigenvectors, stuff like that. And you have a matrix. So every quantum operator is a matrix, and they have to be Hermitian matrix. In the standard, well, I mean, there are people who are exploring non-Hermitian and stuff like that. But in the standard formulation, they have to be Hermitian matrix. Now, if you think about it, what is a matrix? Let's talk about what is a matrix first, because that's really the most important, arguably the most important object in quantum mechanics that you're dealing with, the most important mathematical object. So let's say you have a matrix Aij. So you write A11, A1. Okay, maybe you are seeing this like this. So A11, A12, A13, A21, A22, A23, A31, A32, A33. So this is a square matrix, a 3 by 3 square matrix. It's usually good to talk about square matrix because, well, if you, let's say you have a network with 3 nodes, like 3 points, and there are many possible connections between these 3 points. So to describe all the connections, you actually need a 3 cross 3 matrix. You cannot have a rectangular matrix or something like that. So the first element of the matrix A11 is just telling you how the node 1 is connected to itself. So if you have a 0 in if all the diagonal elements are 0, that means no particle is interacting with itself, roughly speaking, because A11, A22, A33, these are the self interaction terms. If they're 1, that means there is some interaction, depending on whether you're normalized or not. What the elements can be probability amplitudes, the elements can be probabilities depending on how you normalize, stuff like that. A12 is telling you how 1 interacts with 2, so it's from 1 to 2. The corresponding element A21 is telling you how 2 interacts with 1. So if you have a symmetric matrix, so you see, the matrix is actually geometry, because if you have a symmetric matrix, that means A11, A12 is equal to A21. But if you think about it in terms of geometry, that means symmetry. So what what 1 is giving to 2, 2 is giving the same back to 1. See what I mean? So this is just this quantum mechanics, all this formalism, this matrix, linear algebra, stuff like this. This is just a very good, useful mathematical tool to describe what's really happening and to work with these kind of formulas. So it's very handy. But if you say that there is no geometry in quantum mechanics, of course there is no explicit geometry in the sense like as in Einstein's theory, but geometrical insights are all over the place. If you think about path integrals, for instance, Feynman's formulation of quantum mechanics, it's usually introduced as like the sum over path. So you have many possible paths to go from state A to state B, for instance, many possible paths, in principle infinite number of paths. But these paths are weighted, just like in statistical physics we have the Boltzmann weight. So well, okay, let's not get there. That will be because that's my current. So if I start talking about statistical physics, I would make the video unnecessarily long, and that's not really relevant. But in path integrals, what we okay, that's better. In because it's it's like the sun is very bright, so I don't have the blind fully up because it would be, the light would be blinding. But at the same time, I feel a bit more. I just woke up, by the way, just sometime, so I feel a bit more awake if there's at least some sun coming. Anyway, so for the path integral part, you see, you have. I'll just give you the basic idea. I'm not expecting you know about all this. That's not the point. So you can talk about about the different paths connecting A and B, for instance, and but then the question is, not all these paths are equally likely. That's a difference. In statistical physics, we often start with the postulate of equal probabilities. But anyway, sorry, I keep drifting back. So there is a formula, there is a way to find out how likely this path is or how likely that path is. Well, even in statistical physics, this is like the paths that reduce the energy, the free energy, minimize the free energy, are the more likely ones. That's how the Boltzmann weight is constructed, basically. Anyway, sorry. So you have an exponential like e to the power I, where I is the imaginary number, s over h bar. So s is the action. It's just classical physics action. If you don't know what that is, it's just like the difference between your kinetic and potential energies. That's something which we call the Lagrange in classical physics, classical mechanics. No quantum, nothing. And then you take the time integral of this Lagrange. So basically you have a particle which moves from point A to point B. So as it moves, I mean, it has a kinetic energy and it has a potential energy as well. So first of all, you write the general expression of its kinetic energy and the general expression of its potential energy. So like, for instance, if it's an oscillator, the expression for the potential energy would be half kx squared or something. Like, it would be a quadratic function of the position. If it's a, for instance, if it's just a one-dimensional spring, the potential, I mean, then the potential energy of the oscillator would be a quadratic function of position, half kx squared, that kind of form. On the other hand, if it's just a normal particle, like a particle which is falling in gravity, the potential energy would be a linear function of position. You write minus mgx if this is the x direction or whatever. It's a linear function of position. So anyway, you write the general expression for the kinetic and the potential energies, and you subtract it, and you get something which we call the Lagrange. Now the particle is at this point at time t1, let's say, and it's here at time t2. So you integrate this quantity, this difference of the energies, from t1 to t2 with respect to time, and then you get something which is what we call the action. And h bar is Planck's constant, reduced Planck's constant. So it's basically the unit of quantum. So we're dividing s over h bar. That means we're roughly speaking, we're talking about the quantum action. So it's still the same formula as the classical action, but we're dividing it in quantum units. So we're expressing it in units of quantum, right? So this s over h bar, and we're writing exponential e to the I s over h bar. So I is the imaginary number. So this is how we find the weight of each path in the path integral, and then we for every possible path there is a different action, because every path is going through a different position. It has a different like the kinetic and the potential energies that will be different, right? So, and then that's how we find it. But the point I'm trying to say is that if you think about e to the power ix, just mathematics, just geometry, there is no physics here. It's e to the power ix, Euler's formula. It's cos x plus I sin x. Now, what is e to the power ix? Think about a complex plane. You have a x-axis, you have a y-axis. This is the real number line, the horizontal axis, the x-axis, and the y-axis, the vertical axis, is the imaginary number line. So e to the power ix is just a polar form representation of a complex number. You can write it as a plus ib, where it's the Cartesian representation. So a is the x coordinate and b is the y coordinate, and a plus ib is some complex number. So, basically what you will have is like, for instance, if e to the ix, so x is like the amplitude. If you think about cos x plus I sin x, if you break it down in that form, it's the amplitude of the sinusoidal waves. Cos and sin is just some shift, but yeah, basically it's the amplitude. And if there's actually a very good geometrical argument, you can actually find out why, when s is very large as compared to h bar. So for classical bodies like this, massive bodies, for instance, I don't know, for instance, maybe this bottle of water, or even like I don't know, like myself, this window, like for large objects, why do quantum mechanical effects average out? It's not as if quantum mechanics doesn't play a role, but well, it cancels out. Not really cancels out. What I'm saying is that the good way to understand, actually the best way to understand this, is to think about the uncertainty principle always. For me, quantum mechanics starts with the superposition principle, and the uncertainty principle is a direct consequence of the superposition principle. I don't care about Schrodinger's equation. I don't care, I mean, because those are consequences. Those are not the basic, like, not even linear algebra. But for me, the superposition principle is really the most striking feature, because in quantum mechanics, when we say superposition, we mean something very different from the classical superposition principle. This is something which people need to understand, because in classical physics, you can have superposition of waves, but in quantum physics you can also have superposition of waves, but this is very different. Even physically they're different. It's not like that. Yeah, of course they're different because it's classical, it's quantum, but why is quantum so different from classical? The reason is the way the superposition principle actually works in quantum mechanics. I'll not go deep into that in this video. I think I already made a video about this in the past, recent, like a few months back, if I remember correctly. Anyway, So where was I? Yeah, that's the point. Now, so that means even in the path integral formulation, you can have a geometric argument that will show you why the path, like, why basically things become classical in the large action limit. So now these are all, none of this is conclusive evidence, by the way, about the point I'm trying to make, geometry. And this is just a way of looking at the world, by the way. This is not really a physics claim. I'm not claiming that, yes, see, I have found a new theory of physics. I have proved that geometry is more fundamental. That's not what I'm claiming. And there is nothing to prove here. Quantum mechanics, what works is linear algebra and stuff like that, and it's already a successful theory in itself, except for some. So I'm not trying to solve any problem or make any new claims, but I'm just trying to build a new way of looking at everything, and if it makes sense, maybe that's good. If it doesn't, I would like to know your comments. That's why I'm making the video in a way. So the point is, there is still some geometry hidden in quantum mechanics. That's what I'm trying to say basically. And maybe not in the exact same explicit form as in Einstein's theory of gravity, but well, I mean, even if we talk about particle physics, quantum field theory, the extensions of quantum field theory, and then particle physics. I don't know, this is a bit technical, but I don't, maybe not all of you have heard of this, but there is something called the baryon octet, or not just the baryon octet, I mean, stuff like that. So basically, if you plot the different properties of the elementary particles, their mass, their charge ratio, whatever, and you get these geometric shapes. So all of this seems to suggest, maybe I am over claiming, maybe I am over interpreting. I know that. That's why I'm not making any claim. But this seems to suggest that geometry is really more fundamental than just, oh, it's just a mathematical tool. So sometimes algebra works, sometimes geometry works. No, I would say geometry is not just a bit more than that, actually. So one last example I would like to give you before I, let's say, end this video is about, I mean, for to just like not justify, but to kind of relevant to the same point that I'm trying to make is that, well, for instance, we talk in physics, we talk about forces and potential, right? So if there's a real force, if there's a real potential, it's physics. If there's not, well, it's not real physics. Is that so? I mean, my point is, what is a force? A force is the negative gradient of I mean, F is minus du dx in one dimension, whatever. The point is, if you have a potential difference, like the potential is high here, the potential is low here, so that means there's a gradient of potential, then the particle will come rolling down from high to low potential, maybe, I don't know. But to have a force, force means something which is very directed, like we're breaking the symmetry. If there's no force, well, it's perfect, particles are moving everywhere, there is no particular force in one particular direction. But if there's a force, that means there is a gradient in the potential. That's what I'm trying to say, in space, like a spatial gradient. There's high potential here, low potential here, whatever be the case. And then that's why, for instance, in the field of like biological physics, we use many kinds of potentials to model physics, well, like to model the physics of these complex systems. Like we have Lennard-Jones potential. So very simple, very kind of heuristic argument. Not like one term is actually you can derive, but the other term is a bit heuristic. But yeah, the argument is simple, that if two particles come too close, then they will repel. But if they're then there is also, but if they're like sufficiently far, they will attract, and that kind of stuff. It's very simple potential. So the potential well goes like this. I mean, it comes, anyway, I'm not going into that, but it's a very good model when you try to study what happens at the cellular level when many particles like proteins or whatever, they are forming condensate, stuff like that. So it's a very good potential, Lennard-Jones potential. And it's real physics. The people who are doing molecular dynamics, they are using the Lennard-Jones potential because it's a real potential. It's physics. Then you consider people like me who are doing Monte Carlo simulations. Again, I don't want to go into the details, but those of you who know, they already know the difference between molecular dynamics and Monte Carlo simulation. If I put it very simply, in molecular dynamics, it's more about the system itself that you're studying. If you want to study one particular protein or one particular DNA interaction, whatever it is, you actually simulate the system. There are limitations because, like, you cannot go to very big systems because we're actually doing the computation, we're actually making the molecules jiggle around and see what happens. So it's very expensive computationally. You need like lots of like advanced computers, stuff like that. For Monte Carlo guys, I mean for us, basically what we're doing is that we are also studying the similar kinds of systems. For instance, biological systems, protein DNA interactions, stuff like that. But for us, we are not really simulating the system because it's very expensive computationally. It's not really, we're not starting the simulation by adding one particle, two particles, three particles, and there's a limit how far we can go, and then we're seeing how they do. No, that's molecular dynamics. We introduce a potential and we see how that happens. They introduce a real potential, the molecular dynamics guys. We Monte Carlo. We start with statistical physics. So the most ideal argument would be the mean field limit, which means thermodynamic limit, which means we have an infinite number of particles, which is not realistic. That's why we often try to do a numerics versus analytics. So let's say we first of all we try to check using the statistical physics, the calculations, the mean field theory. This is very complicated mathematically, by the way, because it's huge integrals, messy integrals, ugly integrals. You need to do the, for instance, Hubbard-Stratonovich transformation, lots of mathematical theorem, but the final result, when you get it, it's very clean. You can actually see the competition between the physical parameters, how one reinforces the other, how there is, for instance, a positive feedback loop, how there is a self-regulation, self-organization, which is very important in biological systems. It's very important. It's very exciting. But yeah, that's the analytical part, which usually the assumption is always there, hidden, sometimes not explicitly, but the assumption is always there that you're talking about really large systems. Only then statistical, you see what I mean. But then we do Monte Carlo simulations. What is Monte Carlo simulations? You start with a system. Now, maybe not the exact system, you start with a reduced model. Usually, I'm just talking about mostly polymers because that's what I'm working on. But well, there are much more subtleties. I'm not an expert on either Monte Carlo or molecular dynamics. Okay, maybe I'm a bit more comfortable with Monte Carlo than molecular dynamics, but I'm an expert in neither. So the point is, when you do Monte Carlo simulations, what you're actually saying is that you are sampling the configuration space, because there are many possible configurations the molecules can explore. If it's a large system, large enough system, it's huge, like practically an infinite possible number of configurations. So you cannot really do like simulate the exact particles and see what happens. That's not really very practical, especially if you're studying large systems and stuff like that. So it's like an alternative approach. So in Monte Carlo simulations, we simply use Boltzmann's like the statistical physics idea that the most probable or the most likely states at equilibrium are the ones which are the least energy, least free energy, minimization of free energy, and we use that to develop an algorithm to sample the configuration space. And so the system is actually exploring the configuration space, but not explicitly every bit, because that's practically impossible. Then we run to the same problem as them, and that's why we will have a so we sample the configuration space basically, and we attach more weight to those samples which are, well, more likely. How do we determine more likely? By, well, you're at equilibrium, so we do statistical sampling. That's it. Well, that's the philosophy, that's the approach, but there are many more nuances depending on the system you're studying. It's not as simple as that, of course. How do you characterize a phase transition, for instance, if it's a first order, if it's second order, if it is a phase transition at all, first of all. So you collect many data, what to plot. This is a very important skill, by the way, in this kind of research. You have lots of parameters, lots of variables, what to plot against what, and how to interpret that plot, because you could generate millions of plots, but from what plot, what can you interpret, how not to over interpret, or that kind of stuff. But anyway, that's not the point of this video. So recently I came to know about, I was studying the Rouse model, which is simply a model of the polymer. So polymer is a chain, it's like a biological DNA protein, they're all polymers, and Rouse model is simply a model, a mathematical model, which creates a rough simple model of the polymer by saying that it's just some beads, like some beads, which are connected by springs. So there is a bead here, we call it 1, then there is a spring, and there is a bead here, we call it 2, then there is another spring, there is a 3, and then 4, 5, and like this we build a chain. This is again a very simplistic description, because in reality a biological protein or DNA or actual biopolymer, it's not really like explicit beads connected by some strings. No, it's not that, of course. But yeah, this is just a model. And the springs are there because, well, there can be stretching, and as the polymer is doing this whatever, I don't know, there can be stretching and that. And there is something which is always very important in biophysics, which is called mechanochemical coupling. There's a coupling between the mechanical forces, if you try to pull something or push something, and the chemical reactions, because usually for instance, in motor proteins, people are studying motor protein, there is a chemical reaction, ATP hydrolysis, which determines whether, first of all, the protein has to stick to the substrate, lattice gas kind of models, and then it moves forward. But to move forward, there is a chemical reaction which pushes, like determines the step and that kind of stuff. But again, there's a mechanical force, so it's coupled. It's not like which causes which, it's like there's a coupling between both. This is a very common idea in biophysics, by the way. It's not just about mechanochemical coupling. There are many such couplings, some trivial, some non-trivial, but the philosophy is really very common and very useful in biophysics, physics of living matter basically. Right. Now the point is, yeah, sorry, again I got a bit carried away. What I was trying, where was I? Sorry. Yeah. So this is the Rouse model. You have some balls or beads or whatever, and then you have some springs. So you can stretch, and that's how you get a model of a polymer. It's not the real polymer, by the way. It's just a model. But in physics, the idea is to start with simple models. I mean, if you want the exact thing as it is, so you can keep adding more and more complicated terms to your equation, to your Hamiltonian. You can do that, and then what you get ultimately, If you keep adding complex terms, well, at some point you will get the real thing itself. You'll get the real physics. You'll get the real polymer. But you cannot work with such a complicated equation. You cannot make new predictions. You cannot use it to build a theory, for instance, because physics is supposed to be simple. That's the whole philosophy of physics is to, or biophysics for instance, is to find the simplest model that can still recover the non-trivial, the essential behavior of the system. You don't have to recover each and every tiny correction, because to do that you have to compromise the simplicity of the model, which is something that's not usually what we want to do. To make a, because if you have a simple model, a very simple model, then chances are that model is a kind of universal. It's even applicable to systems beyond the system you're studying. But if you want to describe this particular system very deeply and you keep adding term, keep complicating it, then basically you have just built a model that applies only to your system, and even there it's not really easy to work with, so it's not practical, so it's basically useless. That's the philosophy of simplicity, minimalism. Because scaling arguments, for instance, it's crazy. I mean, if you know even a little bit about polymer physics, you will appreciate my what I'm saying right now. My point that even if we start with simple scaling arguments, like just the order of magnitude, we have a effect from the surface, we have an effect from the bulk, the volume, we have this, that. So this should scale as this. That should scale as, so for instance, some variable, some effect should scale as x squared, some other effect should scale as x cube. This is very obvious. Let's say you know this. But the prefactor is an important part after all, because it's ax squared plus bx cube. So what is a, what is b? There is some little bit of physics hiding there. But for the moment, if you completely ignore all the prefactors and just do a scaling estimate, the scaling argument, kind of like a simple, like a dimensional analysis and stuff like that, order of magnitude estimate, you still recover most of the physics and it works, and that's beautiful. Scaling laws, like, sorry, not scaling laws, yeah, the power laws, for instance, power laws. When you have a constraint across scales, this is a bit technical, maybe I shouldn't go into this, because if you're not familiar with these ideas, maybe I'm speaking gibberish to you. But yeah, this is really universal. Universality in physics arises when you have under similar structure, not necessarily for the same system. I mean, that's why we call it universal, but under similar structure. See, you have many constraints across scales, and often you should have a competition between two tendencies like energy and entropy. It's a beautiful example, energy and entropy. If you decrease the internal energy, you decrease the free energy. But if you increase the entropy, you decrease the free energy. And you want to decrease the free energy, basically. So that means the effect that you have when decreasing energy is the same effect that you have when increasing entropy. So they're in a way opposite. But here's the beautiful part. That means if energy decreases, entropy can afford to decrease. Because energy decreasing means you're at low energy, so you're already at low energy, so you don't need to maximize entropy that violently. So maybe entropy can afford to decrease a little bit. So if energy decrease, it's almost as if energy is like, hey entropy, I'm giving you permission to decrease, come down with me. Similarly, if entropy is increasing, entropy is like, I'm increasing, so I'm already stabilizing the system, I'm giving you permission to increase a bit, so the system can get excited. So entropy is like telling energy, come up with me. So that's why they're a beautiful couple, in a way. That's why the way I see it, that's like a beautiful love story in physics. Okay, this is a bit, I was recently having a like a fun discussion with one of my friends, and she was like, we were talking about Kuramoto oscillators, a very, very good model to study synchronization. And you know what, something I will also explore a little bit. And it's really beautiful, because you start with many oscillators. So let's say you start with two oscillators, and they have their own internal frequency, they have their own random phases, they're not identical at all when you start. But in the Kuramoto model, if you simulate, like if you evolve them using the Kuramoto differential equation, after a certain point of time, if they match the threshold, the critical value of the order parameter, then I mean definitely they will synchronize. So that means they will. So let's say initially one is oscillating faster, the other is slower and stuff like that. But then after some point, they will oscillate together in a synchronized fashion, like the same phase difference between them. That's synchronization. And she was like, it's really beautiful, because this is just reminds me of a very good couple. They start from different places, but then their lives meet and they synchronize. And I was like, if you ask me, the best couple in physics is energy and entropy, not statistical. Well, I am a statistical physics guy. I do nonlinear dynamics, my own independent work on emotional modeling. It's mostly nonlinear dynamics. I love Kuramoto kind of models, kind of work. But to me, nonlinear dynamics is a very useful tool. Yeah, but statistical physics is the boss, the ultimate boss, to me at least. Anyway, this is a bit of personal bias maybe here, because of course everything is important, every field is important after all. But the point I'm trying to make is that in the Kuramoto model, you, in your Kuramoto equation, you explicitly add this synchronization term, that sum over all your neighbors and sine of theta j minus theta I. So definitely if your neighbor is faster than you will want to speed up, and if your neighbor is slower than you will want to slow. So you have a explicit term in the differential equation, in the time evolution equation, that enforces this synchronization. The beautiful part is that this model works to describe many real life phenomena. That's why it was built. But I mean, that's the point. Energy entropy, there is no explicit term that wants to make them this. This is the beautiful part, that they're actually opposite. Kuramoto or the two oscillators, they're not really opposite. They have different phases, they have different speeds, like different frequencies, but they're not opposite. But energy entropy by themselves, they have the opposite effect. If I increase, I stabilize the system, says entropy. If I decrease, I stabilize the system, says energy. So their effect is individually opposite, but couple them, and I mean they are coupled in any system with non-zero temperature. Energy and entropy is always coupled, like there is a feedback between them. But couple them, and then they have like kind of like the, okay, if I increase, you can also increase, if I decrease, you have to decrease. So it's like beautiful synchrony, beautiful coupling. But here we don't force any kind of synchronization between energy and entropy. That's what comes out from the statistical, from the partition function, from very simple arguments. We start with the postulate of equal probabilities, which is a very reasonable argument to make at equilibrium. We have also assumed ergodicity, which is again a very reasonable argument for most systems at equilibrium at a large limit. Like if you over sufficiently long time scales, ergodicity is also a reasonable argument for most realistic systems. And well, not even ergodicity, you start with, yeah, okay, and then you from that you get basically Boltzmann's beautiful argument of Boltzmann entropy, and then from there you get this free energy expression. You're not forcing it, you're not forcing anything, but you get this beautiful dance between energy and entropy. That's why I'm like, this is to me the most beautiful love story in the universe, in the world of physics. Is not Kuramoto synchronization, not something else. To me, it's energy and entropy. This is something most of us know roughly, but we don't really my feeling at least is that most of us don't really appreciate. Maybe even the people in the field, like in statistical physics, soft matter physics, stuff, like they always use the energy entropy arguments, but even they don't fully appreciate how beautiful it is actually. I find it very beautiful. Maybe this is a bit might sound a bit weird to you, but yeah, I do find it beautiful, the energy entropy dance. Not in any weird way, but like I told you my reason. And the point I would like to, like, this is my closure basically. I would like to bring it up as a closure before I finish the video. Just a second. Oh my god, it's 10:56. I have to leave for the lab. No, I mean, I just woke up a little bit back, and I just suddenly thought of yesterday night. Also, I was having this thought about geometry and stuff. So I thought maybe let me record a quick YouTube video. And yeah, so after this, I have to have breakfast and stuff, and then go. Well, again, this video was longer than necessary, of course. As usual, once I start talking, I don't have a script and stuff like that. I'm really sorry, by the way, because for my long suffering viewers, and I don't know why some people still choose to come back and watch my videos. I'm forever grateful, but also a bit surprised that anyway. So that's the argument. You see, geometry is completely messed up. The closure, the last point. I was talking about polymers, the Rao's model, beads and springs. Now, if you want to explore the Rao's model, the springs is just for the analytical purpose. It's a very beautiful thing to do, because you can use the formula, like the harmonic kind of expression. Now, but when you want to explore the model numerically, you can start simple. You take a two-dimensional square lattice, just a square grid, a regular lattice, square lattice. And what you do is that you take a square lattice, and what you do is that you do, I'm not sure if I should, because, maybe I can still give you the idea even if you're not an expert. You do a self-avoiding walk on the lattice. So you have a lattice, and I don't know, maybe I should draw. Hold on. Just quickly. I don't know how much of this would be properly visible or even clear to you, but okay. So yeah, I mean, this is like a square lattice. Of course, it's a hand. I just drew it by hand, like a freely. But you see what I'm trying to say. This is a square lattice, and the part that I have darkened, this is like a self-everting walk. So you can think of it as a polymer. A polymer is not really this sharp edges and square. It's more like a, it's more like this actually. If I draw a real polymer, it's more like, it's more like a continuous. But just if you want to model it, you can have a very small lattice with small with high resolution stuff like that. But just as a model, and it's self-everting means it cannot intersect. So see, it's going like this. For instance, it can never do this. Like, you know, it can never from here, it can never come back here, because I mean, it cannot intersect itself. That's what means self-everting. Very simple. So this is a self-everting walk on a two-dimensional square lattice, and this is how we model the polymer. So if you know the length of the polymer, let's say n is 10, so that means it's a 10. So you have 10 balls with springs connecting. So in this as a self-everting walk, you just move 10 steps. 1 2 3 4 5 6, actually 9 steps, because you already start from one ball. So that's how we build the work, just to give you the idea. Now the point, now I don't want to go into details into this, deep into this, but to connect it back to geometry, what I found was that when I was playing with the model, I already have written a like a kind of report, not a paper. It's still not a paper. I'm working on different aspects of it, but like a report, a preliminary report. It's not even a preprint, just a report. I can drop the. You'll find it on my Google Scholar, on my website, on my LinkedIn even, or if you want, if I remember, I'll also drop the link in the description of this video as well. It's public. It's not a problem, and it's just like kind of it's not real research, but it's just, yeah, it is original, but it's more exploratory work. The real work I'm doing is something else. It's a real biological system. That's of course not, I'm working on it, but this is just more. But I think it's very suggestive, because what it did was that when you want to model the polymer, that means the polymer is moving, the polymer is not fixed, the polymer is moving. So there are lots of things that are changing. So to characterize the physics of the polymer, you need to characterize, or like you need some observables. A very good observable, for instance, is the radius of gyration. It gives you a measure of how stretched out the polymer is, or like if a small radius of gyration, it means the polymer is crumpled. If a large radius of gyration, it means the polymer is stretched out. Roughly speaking, coil globule. Okay, that's a different thing. You can also do the end-to-end distance. So the distance between the first bead, or the first monomer, or the first point and the last point, that one. That depends again. Like if the polymer is, for instance, like this, and it's a small end-to-end distance. Otherwise, so you see what I mean. The point, you can also plot how fast the polymer decorrelates, because let's you start and then the polymer can diffuse like this. You have the mean square displacement increasing with time, diffusive or subdiffusive, stuff like that. And I don't want to go into the details, but to make the polymer move on the lattice, because this is a lattice, this is a model, this is not the reality, this is not reality of course, but this is just a model, very good model that works mostly. So to do this, you have some geometric rules. The molecular dynamics guys will introduce potentials. There's a Lennard-Jones potentials between two balls which are attracting or repelling, whatever. Real potential, real physics. Here we don't have any potential, we don't have any force, we have geometry. We say that Monte Carlo simulation is that at random we pick any of the points from this walk, like any of the beats from this chain monomer basically, and we try to move it just randomly. That's the thing about Monte Carlo, about statistics. It's a stochastic like a stochastic process. You choose a monomer, you want to move it randomly. But of course you cannot do whatever you want. So let's say you choose this monomer, and okay, I want to move it here to the next point, or to this here, or maybe this side or that side, whatever. So this is your proposal, but the proposal can either be accepted or be rejected. So when will it be accepted? So because if you want to move one monomer, then the monomers it is connected to will also get dragged, right? Because it's a connected chain, it's not like free particles. So if the distance between your neighbors, let's say I am here, I am holding hands with someone this side, I'm holding hands with another this side, and we are connected. And let's say now I want to move there. So if I move there, then well, they will also feel the pull, right? You see what I mean? Now if this length remains the same, and this length also remains the same, then they're like, okay, the length is not changing, so maybe if you want to move there, go ahead, I have no problem. That's the thing. But if, for instance, if I want to move to some place where if I move, then the length will not remain the same, the distance will not be preserved, the nearest neighbor distance, then they will not allow me to, then this move will be rejected. So based on this, you do this a huge number of times. Each monomer you try to update, and then you move the polymer, and then you get all this. Then basically that's how you model, that's how you simulate it basically. This is a lattice Monte Carlo simulation. There are more realistic, more advanced ways to do it, but this is a very good starting point actually, even if it's pretty simple. And here's the point, it's purely geometric. And well, since we are on a 2D square lattice, so you can only move to the nearest neighbors. Like you just want to move one step, but depending on your nearest, versus the beat which is at the end, like at the first one or the last one, they have very less constant because they're only connected to like this, because if I am the last bit, I don't have anyone to hold this side, so I'm free. I'm just connected to like this. That means I can move there, or because it's just this that I have to preserve. And on a square lattice, I mean, this is the length of the lattice, the edge of the lattice, the one step of the lattice. So let's say I'm this is me, and this is the end, and I'm connected to this, and I have nothing this side. So even if this moves here, so I become this, but this distance between my next and me is still one. If I do this, it's still one, so it's less constraint. But if I'm in the middle, then I have both, and I'm a little bit more constraint, stuff like that. So what I found was that this is the simple algorithm, the one I gave you, that the nearest neighbor distance will always be preserved. But if you want to, for instance, model a polymer that is a bit more excited, it's like, it's very vigorously moving, vibrating, shaking, stretching, stuff like that. But at the same time, you still want to keep the lattice, because without the lattice, the simulations will become very complicated. What can you do? Well, then instead of, because you don't want to introduce a real potential. If you want to introduce a real potential, you don't need any lattice. The potential will do the work of attracting or repelling. That's molecular dynamics. For us, we need some constraints. So if you want more realistic, you can go to like in 3D, for instance, you can do FCC lattice, face-centered cubic, instead of a simple cubic lattice. But point is, you still need these constraints, because geometry. The point. Here's the interesting part. If you play around a bit with the rules, like now, instead of saying that this distance should always be preserved, you can say that, okay, the distance need not be preserved always, but they have to remain within the two nearest neighbors. Like instead of one, you just give it a little bit more relaxed, like more space to explore, as an example. Or maybe you do something more clever. This is what I tried in my report, in my article, actually, which is out. I'll give the link. Maybe you have a polymer, you have a chain, like for instance this chain. So you divide it into two half, like you don't cut it, you don't break it, but in your mind. So let's say this is the first half and this is the second half. So you try to model it in such a way that this is a bit more energetic and this is a bit less energetic. So how to do it? Because here you don't have force, you don't have potential. If you had a real potential, you can say, okay, that let me make the potential much more attractive, or let's say much more repulsive, so that it will be more energetic, it will be more like trying to repel and stuff. But here you don't have anything like that. You don't have real potential, real force, nothing, just geometric constraints. What you can do, you can break the symmetry in time and space. Space, you have already broken the symmetry in space, because you're saying the first half behaves different from the second half. In space, in time, simple thing you can try is that in Monte Carlo sampling, first of all, you choose a monomer or a bead or a point within the chain in random, and you try to update it. But the thing about Monte Carlo, in usual Monte Carlo, is that on average you want to choose, like in one Monte Carlo sweep, something which we call sweep, in one sweep on average you want to choose all the monomers at least once. That means if there are n monomers, there are n attempts to update on average, n attempts to update per sweep. But if you do a large number of sweeps, then on average you do everything. In one particular sweep, it's not necessary that you have to do like all the n. Maybe you do n, but some are getting chosen thrice, but two are getting left out. That can happen, for instance. Now that's the thing. But if I slightly play around with the rules, and if I say that, oh, okay, wait, what if this is the first half, which is a bit more energetic, and this is the second half, which is a bit less energetic, but how do I enforce this more or less energetic, because I don't have a real force, a real potential? I say that I write the Monte Carlo algorithm in such a way that the first half is being chosen more frequently. So let's say this set of monomers in the first half are twice as likely to be chosen as this. I could make it thrice, 4 times, 1.5 times, whatever. Then automatically they will move a bit more than this, simply because they are being chosen to move more. Some of them will be accepted, definitely. That is the thing. So just by playing around with the geometry, what I found was that, okay, maybe I should actually give the link in the description, because otherwise I'll not be able to, I cannot show you all the results right now. Yeah. I don't have it print. I have a print a copy of it, but it's in my lab, and it's right now I cannot show you anything. But what I found out was that I plotted all this, like for instance, radius of gyration as a function of time, or the diffusion, like the mean square displacement as a function of time. What I found was that this simple model, where I just played around with the geometric rules a little bit, like made something more likely to be chosen, or break the symmetry and stuff, without introducing any kind of real physics, force, or potential, I found something beautiful. I found that the polymer is, under some situations, the polymer is doing something very unphysical, which is, okay, maybe I chose the wrong constraints, because I'm just playing around. I don't have any real physics data or anything at this point, for this model at least. But sometimes the polymer is kind of expanding, then contracting, expanding and contracting, expanding and contracting. So how do I know it's doing that? Because the radius of gyration squared, usually plot the square, time. So it's doing this. So it's always between one value which is high, one value which is low. It's fluctuating between those two values. Sometimes it stays a bit high, then it comes low, and then, so that means when it's high radius of gyration, that means it's expanding, it's in an expanded state. But then again it collapses to a low radius of gyration, that means it collapsed, then again it's moving on. So it's doing this basically, roughly speaking. And this is a very, like, this kind of things are observed in real biological systems. Then for instance, sometimes I see that the radius of, or like not just the radius of gyration, but sometimes the polymer cannot freely diffuse. It diffuses a little bit, but then instead of becoming freely diffusive as we would expect in the traditional Rouse model, it plateaus a bit, and that's not always due to finite size effect, but also due to static repulsion. Because that's in a way, because when you're in a cell, it's very crowded with lots of intracellular organelles and stuff like that. So maybe you have energy, you want to move, but you are surrounded by other particles, or other, like for instance the mitochondria, Golgi apparatus. I don't know much about biology, but whatever. So you cannot really freely move, you're constrained. But in our model, we are not actually introducing a real massive particle, a real massive crowder molecules, or any kind of stuff like that, a real potential force. We have geometry and nothing else. But if I am choosing something less frequently, geometrically, you can think about it physically. That means, okay, maybe that part is a bit crowded, surrounded by stuff. That's why they're not able to move. But to translate it to the language of geometry, okay, just choose it less frequently. So just by doing this, what I found was that I found many interesting real physical effects which people do when they do, for instance, more explicit like potentials and forces. Now the point is not to say that that's not important. That's, of course, if you want the real physics, you have to go their way. But the point is, if I can get this without using that at all, just by changing geometric rules, it's not really surprising, but it still seems to suggest that geometry is maybe more like, because force is geometry. Gravity is the best example, but even in general, like force is like a potential gradient. You see what I'm saying? Intuitively, it appears, at least to me, that geometry is really very more fundamental than we realize. Of course, geometry, algebra, everything is important. Like the reason I said geometry is I think it's more closer to group theory. I also did some work at one point of time on modular groups. So in mathematics, you have a group. Group in mathematics is very complicated. It's not like, but again, I cannot go into group theory here. It's already, I have to end the video now. It's already 57 minutes. So group is just a mathematical group, and then you can have groups have a fundamental domain, which means it's possible that there is a mathematical transformation that transforms every element on the group to a unique element, like a unique transformation to some element in the fundamental domain. Like, I mean, two different elements in the set can be transformed to the same element in the fundamental domain, but by different unique transformations. That's how you define, like, this is all to do with group theory. But the point is that it's people in high energy physics. I studied modular group first. It has many applications in neutrino mixing and high energy physics, beyond standard model physics, stuff like that. And well, it's geometry at the end of the day. You observe some patterns in neutrino, even in standard model. You observe some arbitrary numbers, like why do the quark ratios go like this, stuff like that. It's geometry. Baryon octet, I already told you about. So well, this is the picture is not totally clear. Standard model, lots of open questions, unanswered questions. But the point I'm saying is that, I mean, I have said it enough number of times, I believe, already at this point. Maybe geometry is always there, sometimes in a less explicit form, so it's not obvious. It's not always as explicit as general relativity, Einstein's theory. But yeah, my little experience in physics and my thoughts, my personal, seems to suggest that, well, geometry is really fundamental. So, well, I mean, if you were to ask me that you can use only one tool for the rest of your life and you have to let go of either geometry or algebra, maybe algebra. Okay, I don't know. That's not the point. I'm not trying to like compare, or it's not like geometry versus the rest of like algebra. Nothing like that. But I just wanted to say that, okay, maybe this is a very, very important way to think about geometry. It's way more fundamental, and maybe there is some real physics hiding there as well. I don't know. I would like to hear your thoughts. But yeah, I think that's enough for this video. Thanks for watching.